Okay, so the plan for today is just to continue with chapter 4 probability. Um, there are 3 PowerPoint presentations for chapter 4. They're all on Blackboard. I also posted them in the chat so you have easier access to them. Um, so we're just going to continue on with part 1 today, work our way into part 2, maybe get to part 3, maybe just finish up part 2. Um, so that's the plan for today, and at least the next class meeting will be to continue working through chapter 4. Just a reminder, the Unit 1 exam is this week. Make sure that you take it within the allotted time window. So it was available this past Monday at 9 a.m. and it's available through this coming Sunday at 11:59 p.m. The materials chapters 1 through 3 and the sample exam has been available so you can get an idea of what the type of questions are that will be on there, what the length of the exam is, and so on. No Proctor U for the first exam. I'm actually meeting with our kind of Proctor U lead tomorrow, and we're gonna sort out some of the tech, make sure everything's working right. So that definitely should be up and running for the second exam. I probably shouldn't say it will definitely be up and running. Number one, you know, nothing is a certainty in real life. See last lecture's discussion of probability, but also, so ideally things will be uh, up for the second exam. We don't want to jinx it. Um, and as I mentioned, there's a syllabus policy. There are no due date extensions on the exams. Make sure that you take the exam well before the due date and time of Sunday at 11:59. I would recommend planning to take it on or before tomorrow night, Thursday night. That way, if anything goes wrong, if there's a tech issue, a power outage, personal something or other comes up, like whatever it may be, you have a full business day to get that sorted out, as well as a couple weekend days for buffer. And just a reminder, there is some material posted in the supplemental materials folder, an exam 1 formula sheet that you're welcome to use on the exam, chapter 4 PowerPoints, and I posted a couple of programming examples for those who are interested. Again, not in any way a requirement for the course or an expectation for the course, but I know there were folks who mentioned being interested in data analytics and programming and IT. So if that interests you, feel free to take a look at those. That was just an example of making some box plots using some different technologies. Okay, since I forgot the quote of the day last time, we have 2 quotes of the day today. One of them particularly relevant to stats, the idea that one physical test is worth 1,000 expert opinions. So in other words, this just gets at the idea that most of our sciences, say physics or chemistry or biology, are empirical sciences. So we have models, we have ideas and theories and so on that we try to use to simplify a complex system and make it easier for us to maybe understand it a little bit better or some facet of it or make predictions. Um, but those models are necessarily limited. And if we come up with a model, it doesn't matter how nice that model is or how much we really feel like it ought to be true. It doesn't even matter who says this is a good model, whether that person has this degree or that degree or this accolade or that accolade. Uh, if it disagrees with experiment, if I say this model predicts this thing in physics or in chemistry and biology and it doesn't, then that model's wrong. Of course, with some caveats, maybe we prefer a simpler model that's a bit less accurate over a more complex model that's more accurate when we don't need that accuracy. So of course, the black and white of right and wrong, there's some gray area there as well. But in short, in the experimental sciences, the the arbiter of truth, as you might call it, is testing against the real world. In mathematics and mathematics proper, there's not really an arbiter of truth. We say these are the assumptions that we're gonna set up. Do you not like those assumptions? Well, I mean, okay, you can not like those assumptions, but these are the assumptions we're using. If you wanted to use different assumptions, you could, and you could build your own structure of mathematics, and maybe you would find that more interesting. But these are the assumptions we're using, and then we're applying this set of logical rules and we're building off of those assumptions, making theorems, making conclusions, and so on, connecting things together. Um, So you can't look at mathematics and say, well, those are, bad assumptions to make. It's, well, they're just the assumptions that are made. Now, of course, in math, there's always, mathematicians exist in the real world. We need to make money and, be able to buy food and so on. So there is a sense in which, well, there's going to be a bias towards choosing assumptions and reaching conclusions that are more readily applicable to the real world. Um, oh, I just saw a question in chat. Yes, there will be sample exams before the other exams as well. Yep, definitely. So, so when we make a set of assumptions and build a structure off of that, typically that's going to be biased towards assumptions and structures that explain something in the real world that people might want help explaining. Um, and I think this is particularly valid for what we're discussing today and in the next couple lectures, because we've made this switch from the very empirical side of things in chapters 2 and 3, looking directly at the so-called real world data, to flipping the switch completely out the other way and looking at this purely, in theory, purely abstract idea of probability. And I mean, obviously, we're not just building up the structure of probability for no reason. We eventually have in the back of our minds, we're probably going to want to apply this to something in the real world to help us understand that a little better. I don't know why it is like my allergies won't bother me all morning, and as soon as I start talking, they start to go haywire. Sorry. So anyway, so we're building up this structure, and from one point of view, the structure is a completely abstract structure, the idea of probability. Um, but of course, we kind of are thinking in the long term, we're eventually going to be connecting this back to the real world. So for the time being, we're thinking of this as a purely mathematical structure, and in truth, it is. But we will, kind of between chapters 6 and 8, be tying these two ideas together. We'll be bringing this model into the real world, trying to bring it to bear on some of our problems that we're trying to solve. And sorry.
Bless you.
Thanks. This is always the time of year when it starts getting like warm and cold, between the day and night, either in the fall or in the spring. That's whenever my allergies start going haywire. Um, anyway, so we will of course be trying to marry these two things. And the third point that I want to make is that's where this kind of interesting philosophical complexity comes about, where, well, if I have this model and I apply it to the real world and I'm saying something about the real world, sometimes, like in physics, I have very clear claims that I'm making. If I throw a ball at this velocity, at this speed, in this direction, this is where it will end up. And I can throw the ball and I can test where it end up. If I'm making a claim like, well, there's a 30% chance that it'll rain tomorrow. Well, if it rains tomorrow, I mean, that's within the realm of possibilities under my model. If it doesn't rain tomorrow, that's also within the realm of possibilities under my model. If I say there's a 30% chance or a 90% chance or a 10% chance, those seem to be different claims, but just observing what happens tomorrow doesn't, support or refute that claim. So the discussion of what do we actually mean in the real world when we say the probability of an event is such and such is a deeper question, and we'll have to, I shouldn't say we have to. I think actually in most classes they just ignore that question, but I think it's important to at least address that question and look at a couple of the different perspectives. Okay, give me 1 second here. Okay, and then Quote of the day number 2 comes from my favorite professor, one of my professors in grad school. He's now retired, Professor Bill Layton. And one of his quotes that stuck with me was this idea that good decisions come with experience. How do you get experience? Well, experience comes from making bad decisions. So good decisions come from making bad decisions and reflecting on why that was a bad decision. Um, I think there's also a bit of a caveat to this, that there's a saying that goes something along the lines of wisdom is learning from other people's mistakes. So letting other people make bad decisions, seeing that, and then analyzing their bad decisions as well as your own can really leverage, um, your ability to make good decisions. There's a channel on YouTube that I watch every once in a while, and this guy does climbing fails. So my wife and I do rock climbing in a gym. We don't do the outside, crazy rock climbing, but so I watch him every once in a while, and he'll, go through 3 or 4 different clips where people are climbing. It's usually outside, and they do something dumb and then they get hurt. Not even dumb always, but but it's always, he always looks at it from the perspective of, okay, they did this, it ended up badly for them. Sometimes it's just kind of bad luck. It's like, okay, well, that just stinks, like that's just bad luck. But often it's, okay, well, they could have done this thing differently, or they could have been more careful this way, or they could have evaluated the risk, a little bit differently. It's always easy to say in hindsight, of course, so it's not blaming the person, um, but you can always take something away from, okay, that went south, you know, what can we take away from that to make that less likely to happen to us in the future, so that, you know, I can learn through their pain and not through my pain, when possible. Okay, so I think that is all of the that's everything I wanted to get through. Yeah. So jumping over now to our PowerPoint. Before we start, are there any questions on anything? Any questions on the material from last time, on the homework, anything like that? Okay. Okay, so we talked briefly before about some ideas related to the addition rule, particularly the complement of an event. So an event, so just quick recap, a sample space is the set of all outcomes. So we have a probability experiment. We might think of something like rolling a die or flipping a coin. The sample space might be something like 1, 2, 3, 4, 5, 6 for rolling a die, or heads, tails for rolling a coin. An event is a set of outcomes, a collection of outcomes. It could be all of the outcomes in the sample space. It could be no outcomes that are in the event. But typically we think of a typical event as having some, but not all of the outcomes in the event. So maybe something like rolling an odd number on a die or flipping a tails on a coin, something like that. The complement of an event, the complementary event, denoted one of these 3 ways. I usually use E superscript C for E complement. It's the set of outcomes that are in the sample space, but not in the event E. We talked about a diagrammatic approach to modeling this with a Venn diagram. The rectangle represents our sample space, so we kind of imagine all of the outcomes in the sample space are in the rectangle. And we typically draw circles inside the rectangle to represent events. So this event E is represented by the circle. Some of the outcomes in the sample space are inside of that circle. Some of the outcomes in the sample space are not inside of that circle, not in the event. And those outcomes that are not in the circle for E, but are in the box for the sample space, that collection of outcomes is the complement E complement. Note that the size of the rectangle, the size of the circle, the relative sizes, anything like that is completely irrelevant. This is just kind of a schematic picture. It's not meant to be any kind of, it's not like a bigger circle for E means that event is more likely, or a smaller circle, it's less likely, something like that. It's just a kind of schematic. So one example if event E is rolling an odd number, that's the collection of outcomes 1, 3, 5. Those would be the outcomes that are in the event in the circle. And then outside the circle, but still in the sample space, would be the other outcomes, 2, 4, 6. That would be considered the complementary event to rolling an odd number. So an event is really just a collection of outcomes, but we often prefer to refer to events using some kind of narrative, right? So instead of saying event E is the collection of outcomes 1, 3, 5, we might just describe that as rolling an odd number. And I think we intuitively understand that if we don't roll an odd number, and if we roll a positive integer, then we must get an even number. So the complementary event would be the even numbers, or the even numbers from 1 through 6 are 2, 4, 6. So strictly speaking, an event is just a collection of outcomes, but most of the time when we refer to an event, we refer to it in kind of a narrative fashion. We kind of describe it in words, and then that describes some outcomes that are in that event. And we talked about the complementary events rule, that the probability of an event is 1 minus the probability of its complement. So we're rehashing a couple of little details from last time. That's why I'm going through this a bit more quickly. If you missed last time, take a look back at that for a more thorough discussion of this. But I'm going through this pretty quickly. We looked at an example where this was more work than it was worth, certainly, to use the complementary events rule, but we were just doing this to get a little bit of practice. We had an example where it saved us a little bit of time. Instead of having to count the numbers bigger or equal to 2, 2, 3, 4, 5, 6, we could write it as that probability is 1 minus probability of the complementary event, just 1 minus probability of rolling a 1, and there's only one way to roll a 1. So 1 minus 1/6, 5/6. Saved us a little bit of time, but probably, again, not worth the trade-off. But we often see cases where in more complex scenarios, the trade-off is definitely worth it. So we talked about the rolling a sum greater than or equal to 4 on a roll of 3 dice. There are lots of different outcomes, lots of different die 1, die 2, die 3 combinations that will result in a sum bigger than or equal to 4. But if we rewrite this as 1 minus probability of rolling a sum strictly less than 4, I can either get a number bigger than or equal to 4, or the complement of that is getting a number strictly less than 4, so I don't want to include 4 here as well. Well, there's only one way to roll a sum strictly less than 4 with 3 dice. That's getting a 1 on each of the 3 dice. If I even get, 1, 1, 2, I'm already at 4. I already have a sum that's bigger than or equal to 4. So there's only one outcome in the sample space that has a sum strictly less than 4, and there are 6 cubed outcomes in the sample space overall. So this probability is 1 minus 1 over 6 cubed, or about 99.5%. This was definitely easier to count the number of ways I can roll a sum strictly less than 4 than the number of ways I can roll a sum bigger than or equal to 4. That would have been, very, very difficult to count. So I think this is about where we left off last time. Any questions on that? So this complementary events idea, really important idea for both simplifying hard problems, and actually as we move into, say, like chapter 6, it's going to be an important idea there as well. Okay, so moving on then to the addition rule. So we need one more idea before we get to the proper addition rule, but we can say that two events are mutually exclusive if they cannot both occur at the same time. In other words, if they have no outcomes in common. So for instance, rolling a 3 on a die, that could be one event. Rolling an even number on a die, that could be a different event. These are mutually exclusive events. There's no way to simultaneously roll a 3 and an even number on the same trial. As opposed to, say, rolling a 3 and rolling an odd number. Well, I suppose I could roll an odd number that's not a 3, like if I roll a 1, but I could roll an odd number that is a 3, and I could satisfy both events at the same time. but I could not satisfy the event rolling a 3 and the event rolling an even number at the same time on the same roll. If we look at, say intramural activities, playing basketball and being in the chess club, probably not mutually exclusive events. It's probably feasible that somebody could participate in both of those. So the addition rule. When we have two events that are mutually exclusive, then we can say that probability of A or B equals probability of A plus probability of B. So we can model mutually exclusive events using a Venn diagram. I have event A, and I have event B where there's no intersection between them, right? All of my outcomes that are in event A are not in event B, and all of the outcomes in event B are not in event A. They're mutually exclusive, and maybe there are some outcomes that are in neither of them. But there's no overlap between these circles, between these events. In this case, probability of A or B is probability of A plus probability of B. We just add the two probabilities together. The or conjunction is kind of related to addition. Something like probability distributes over or as addition, more or less. And this makes sense, right? If I think what's probability of A or B, it's the number of outcomes in the event A or B, number of outcomes in A or B. Well, that's of course just number of outcomes in A plus number of outcomes in B. In this case, it looks like I have 5 outcomes in A, 3 in B, right? So those numbers add together. And then, of course, divided by number of outcomes in the sample space across all of them. But we see that number in A or B is number in A plus number in B. And of course, divided by number in the sample space for all of these. So what do we get if two events are not mutually exclusive? So I have event A, I have event B. I have some outcomes that are only in A and not in B. I have some that are in B and not in A, some that are in neither, but I have some outcomes that are in both A and B. Right? I might have some students who both are on the basketball team and play and participate in the chess club. Well, what is probability of A or B then? That's the number of outcomes in A or B. In other words, that would be like this one, this one, this one, these as well, but also these. When we say or, we mean the inclusive or, as opposed to the exclusive or. In other words, we mean A or B or both. As opposed to the exclusive or, which is A or B, but not both. So exactly one of the two. Exclusive or is used a lot in computer science. And actually, I think we have some computer science folks in here. So if you're interested in programming, that your programs get compiled to, well, depending on what language you're using, but for compiled languages, they get compiled to assembly code. And if you ever look at your assembly code, you'll see that sometimes, well, not inclusive or, but sometimes you'll see it come up with this XOR operation. And it turns out that in some processors, XORing a memory address with itself to clear it out is a little bit quicker than just setting that memory address to 0. So just interesting little programming tidbit for those interested in computing and programming and all that. So if you look at your assembly language and you're like, wait, why is there an XOR there? Like, that might be what it's doing. If it's like XOR whatever, EAX comma EAX, that's probably what it's doing. It's setting that address to 0, and it's a little bit quicker on some architectures. But we're not using XOR here, we're using the inclusive OR, meaning A or B or both. So if I look at this, if I were to, and of course, divided by number in the sample space, but if I were to say number in A plus number in B, in other words, if I go and I count all of the outcomes that are in A, I get these 3, but also these 3 are in A too, right? And then if I were to count the number in B, well, I count these, but I would double count these ones in the middle here. I'd count them with the A's, and I'd count those outcomes again with the B's. So I actually need to subtract them off once. Right? If I have overlap between events A and B, if there are outcomes in both, when I say how many outcomes are there in A, I get that number. When I say how many are in B, I get that number. But that sum has double counted any of the outcomes here in the intersection. So to remedy the double counting, I need to subtract off one of those. I need to subtract off the number in both. So the more general addition rule, if we don't have the special case where our events are mutually exclusive, is probability of A or B is probability of A plus probability of B, but this has double counted anything that's in the intersection, so minus probability of A and B. So the net, we only count each of those outcomes once. Okay, so what's the probability of, say, rolling a 1 or a 3? So probability of event rolling a 1 or event rolling a 3. Well, these are mutually exclusive. On a given roll, I cannot get the outcome 1 and also get the outcome 3. They're different outcomes. I can apply my addition rule for mutually exclusive events. This is probability of rolling a 1 plus probability of rolling a 3. 1/6 plus 1/6 is 1/3, or 33%. And of course, this is what we would expect, right? 1 or 3 has 2 outcomes in it out of 6, so we'd expect 2/6 or 1/3. We can model that with a Venn diagram like this. Event 1 is rolling 1, event 2 is rolling a 3. These are disjoint. These circles do not overlap one another. There's no outcome in common between the two. On the other hand, we could have a situation that's more like this one here. So we have, I don't know why that, I don't know, my alignment got a little bit wonky here on this slide, but suppose the roster for the chess club at a school is Alex, Bob, Chelsea, and Dave, so A, B, C, D, and that the roster for the basketball team is Alex, Dave, Ed, Frank, Gary, and Henry. Suppose there are 50 kids in the school, and our school only enrolls students with the first name that's not already taken by somebody in our school, so all of them have unique first names. What's the probability that a randomly chosen student is in the chess club or on the basketball team? So what do I have over here? I have a Venn diagram. I have my chess club. I'm going to put this C in a box because I want to be able to refer to Chelsea with just the C. And basketball team, I'll put that in a box as well. That just means basketball team. So I can refer to Bob with just a B. Okay, so if I look at what I don't want to do is I don't want to say, well, okay, chess club A, B, C, D, and go and write A, B, C, D, because for each of these, I want to keep track of also whether they're on the basketball team. So I'm going to look at each outcome individually. So for Alex, well, Alex is actually on both chess club and basketball team. Alex is in the middle here. Bob is only on the chess club. Chelsea only in the chess club. Dave in both. Ed, Frank, Gary, and Henry on the basketball team. And then that's 1, 2, 3, 4, 5, 6, 7, 8. And then there would be 42 more students who are outside here that are not in the chess club and not on the basketball team. Why aren't we like in a club and on a team? I don't know. Seems like we should be in a club and in a team, or on a club and on a team, but uh, random things about, your native language that you never really think about. So there are 42 other students that are outside of here. So what is the probability of chess club or basketball team? Well, that's the number that are in the chess club or the basketball team. That's 1, 2, 3, 4, 5, 6, 7, 8. So there should be 8 out of 50 or 16%. So we drew this out schematically. This worked okay because we had a small number of folks to look at, but we want to generalize this, right? We want to make it work for more general cases where I have maybe lots more outcomes, something like that, where I don't want to draw out a Venn diagram and go through and count everything. So let's make sure this works. What's the probability of somebody being on the chess club? Well, that's the number in the chess club. So how many are in the chess club? Alex, Bob, Chelsea, and Dave. That's 4 out of 50. Plus how many are on the basketball team? That's 1, 2, 3, 4, 5, 6 out of 50. And here I've counted Alex and Dave both in the chess club. So among that 4 out of 50, and on the basketball team, among that 6 out of 50, I've counted them twice. I have to subtract off the probability that somebody is on both the chess club and the basketball team. Well, that's 2 outcomes in common between them out of 50. Or 6 plus 4 is 10 minus 2 is 8. 8 out of 50. That looks good. So what we got by counting is the same we got by our little formula down here. And kind of as an aside, I want to point out that if we don't know if 2 events are mutually exclusive or not, well, by default, we can just use the second one, right? Because if the events end up being mutually exclusive and we use the second one, what does it mean for them to be mutually exclusive? Well, that just means the probability of A and B, or the number of outcomes in the intersection of A and B, is 0. So if this ended up being mutually exclusive, this bit would just be 0, and then I recover my simpler formula. So basically, the second formula is the more general formula. It applies to all cases, but sometimes I'm in a really nice case where I have mutual exclusivity, and then I can apply a simpler formula. So this first formula is really just a special case. It's a nicer case. The second formula is really the more general case. It encapsulates the first case as well. But if we can get away with using the simpler formula, we probably want to do that. Okay, so this is what I just drew out over here. So any questions on that problem before we move on to the next one? Okay, so I was reading an article several years back now, and it reported these numbers, and I thought these were kind of interesting numbers. So I think a lot of people would have looked at this and thought that maybe there was a typo, or maybe something was wrong with their survey data or something. But they said there was a study done that collected data on pet ownership, and it reported the following results: that 37% of US homes own at least one dog, 30% of US homes own at least one cat, and 60% of US homes own at least one pet, cat or dog. I think a lot of people would look at this and just kind of intuitively think, oh, well, wait, 37 plus 30 is 67, but you're saying 60% own at least one pet. I think there was a mistake there, right? Oops, the numbers don't add up. Let's look at what's happening here. So I'm going to draw a Venn diagram, and we know that there are folks who own cats. We know there are folks who own dogs, but there are also folks who own both cats and dogs, or at least one cat and at least one dog. My circles are becoming more like ellipses now to make that intersection just a little bit nicer to kind of write in. So my left circle or ellipse or whatever is cats. So this entire black ellipse here is folks who own cats. If I look at a household and they own at least one cat, they're in that ellipse, whether or not they own dogs. This ellipse on the right is the dog owners. If I look at a household and there's at least one dog in that house, then that household is in this ellipse on the right. So this kind of like, I don't know, kind of like Pac-Man shape over here on the left, this is cats only. In other words, this region on the left that's like part of that left ellipse with part of it cut out, these are the households that own at least one cat and no dogs. So these folks own a cat or cats and no dogs. On the right over here, this kind of right side, like somewhat Pac-Man shape, these are the dog only households. These are the households you look at them and they have at least one dog and they also have no cats. And this region in the middle here, I'm not coloring it red on purpose, but you know, if you own cats and dogs, they might not get along so well. I don't know. These are the households that are both in the cat ellipse and in the dog ellipse. These are the households that own cat and dog. And then lastly, there are going to be some households that are in neither of these ellipses out here in this kind of no man's land in the sample space. These would be no cat and no dog out here. So that's what our four regions represent. I have events, cat and dog, where owns at least one cat, owns at least one dog, but they segment the sample space into four regions. People who only own cats, in other words, cat and no dog. People who only own dogs, they own a dog, at least one dog, and no cats. Households that own at least one cat and at least one dog, and households that do not own a cat and do not own a dog. So what I actually see is that the folks who own at least one pet, let me give these kind of maybe Roman numeral names. We'll call this region 1, this region 2, and this region 3. I see that region 1 plus region 2 plus region 3 is associated with people who own a pet. I see that region 1 plus region 2 is associated with people who own a cat, and region 2 plus region 3 is associated with people who own a dog. And now I really see what's happening is that in that 60%, that's looking at all of the pet owners. But if I were to do 37% plus 30%, if I just added those two together, I would be double counting region two. I'd be double counting the households that own a cat and a dog. And I can actually just kind of intuitively figure out, well, if I just naively did 37 plus 30, I get 67. I should have got 60. How much did I double count? Region two has to be 7%. There have to be 7% of people who own both a cat and a dog. And then I know that there are 37% that own at least one dog. So that means 7 percentage points of those folks own both a cat and a dog. So then 30% own only a dog, or in region three, and 30% of homes own at least one cat. 7 percentage points of those are the folks who also own a dog. So 23% have to be region one, the cat only folks. So 7% of households own both, 30%. So dog only is 30%, and cat only is 23%. And this was the Venn diagram that I drew. We went through this kind of intuitively based on the Venn diagram and just kind of thinking about what was forced from that 30, 37, and 60. We could also go through it very algebraically and algorithmically with something like this. Probability of cat or dog is probability of cat plus probability of dog minus probability of cat and dog. So 60% equals 30% plus 37% minus probability of cat and dog. Solve for probability of cat and dog. And that gives me 7% for the probability of both. And then we could look at what's the probability somebody owns at least one dog and no cats. So probability of dog and no cats. So this kind of right sector over here, this one that I've labeled Roman numeral 3, or the dog only. So these are the outcomes that are in the dog ellipse, but not in the cat ellipse. Well, this is probability of dog. These are all of the folks in the dog ellipse minus that intersection, probability of dog and cat. 37 minus 7 is 30%. And then similarly for the cat only folks. So we could go through this very carefully with all of the algebra and all of that, or we could really lean heavily on the Venn diagram to get us to the same answers. Any questions on any of this? Okay, so that finishes up part one and the addition rule. Let's jump over to part two. So interesting little quote by Isaac Newton. Obviously one of the brightest minds probably in history, came up with calculus, came up with Newton's laws, all kinds of, all kinds of things that he discovered or invented or created or whatever you may call it. There are lots of people who like to debate about whether, for instance, mathematics is created or discovered, or what parts of mathematics are created versus discovered, and so on. But so Newton says, to myself, I seem to have only been like a boy playing on the seashore, diverting myself now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. So again, just reminding ourselves that, we're making these models, we're finding these little pebbles or nice seashells, and they don't actually represent the truth of what's going on. This is a model that we overlay onto the real world to help us maybe understand it a little better, or maybe make predictions a little more accurately. But we shouldn't think that our models of the real world are actually the truth. The arbiter of truth is the real world, the experiment. Our models are an attempt to understand that a little bit better. So we'll take a little bit of a just kind of fun diversion here, because I know this probability stuff is pretty dry. Uh, even for even for math standards, it's somewhat dry. And we'll look at probability and risk. This is a selection of some experiments that were done by two guys, Kahneman and Tversky, I think roughly in the 70s, 60s, 70s, 80s. So guys who looked at how people actually take ideas like probability and so on, and incorporate that into the decision-making processes. So how do we make decisions under uncertainty? And this was one of the experiments they did. They said, okay, you can enter one of two lotteries. Lottery A, 90% chance of winning $2,000, 10% chance of winning $0. Or lottery B, 45% chance of winning $4,000, 55% chance of winning $0. Which one would you choose? So think about it for a second. You don't have to pay to enter the lottery. You just, you walk up to whatever, event that you're at, and there's two tables for door prizes. You can pick, this or that ticket. You can pick a ticket for this lottery or a ticket for that lottery. And they asked a similar question. You can enter one of two lotteries. Lottery A, $2,000 winnings with a probability of 0.002, $0 with probability of 0.998, or lottery B, $4,000 with probability of 0.001, and 0 with probability of 0.999. So which one would you choose here? And the pretty typical, so in theory, now that we've discussed probability and statistics a little bit in the past, you might be looking at this and saying, hey, wait, I either have a 90% chance of 2,000 versus a 45% chance of 4,000, versus a 2 in 1,000 chance of 2,000, or a 1 in 1,000 chance of 4,000. I have, in both cases, half the chance to win twice as much, right? So you might be looking at this now with a more critical eye and saying, well, these are basically the same lottery, right? Would you cut your chances of winning in half in order to win a prize that's twice as big? So as a general rule, people who choose 1A mathematically should choose 2A, and people who choose 1B should choose 2B. It's not saying that, the higher probability is always the better way to go. It's not saying that the higher winnings is always the better way to go. But if you've made a decision that you prefer the higher probability in one case, you probably should prefer it in the other case. And if you've made a decision you prefer the higher winnings in one case, you should prefer it in the other case, at least according to economic theory. Well, economic theory prevalent at the time. But often people choose 1A and 2B. And kind of what's the explanation of that? Well, when we look at numbers like like 2 in 1,000 or 1 in 1,000, we say, I'm not going to win anyway. If I'm probably not going to win, why not, shoot for the moon? Why not try for the higher number? I basically look at this and say, it's a lost cause anyway. I'll shoot for the higher number. But this lottery up here, I look at 90% and I think, that's like almost a sure thing. I'd really feel like a goofball if I switch to the other lottery. I'm basically guaranteed $2,000 from my perspective. But if I switch to the other lottery where I have less than 50% chance of winning. It's more likely I lose than win. If I switch to that to try to get $4,000 and ended up losing $2,000, like I'd feel like a goof, you know? So I think that's the thought process that goes through a lot of people's minds. They look at this as essentially a guarantee of $2,000 versus more likely than not of losing if they try for the 4,000. But for two in 1,000 versus 1 in 1,000, they basically see that as essentially impossible to win either way. Might as well try for the 4,000. Um, so as a general rule, when we're looking at outliers and we're looking at very rare events, people aren't very good at making accurate judgments in the presence of outliers. And Nassim Taleb ran a hedge fund for a long time, and this is what he did. He would, say he would bet on way out of the money options. So he'd say, whenever this stock is trading at $30, he would offer somebody to make a contract with them that he could buy the stock, at any point in the next 3 months for, I don't know, $60 a share from them. And of course, like if the stock's trading at $30, he's not going to buy it from them at $60. So they said they're looking at this and saying, okay, if the stock goes to $75 a share, then they've got a problem because then he can buy it from them at 60, but they'd have to buy it off the market at 75 to supply it. They would lose money. He would make money because he could buy it at 60 and sell it at 75. In reality, they would just exchange the cash equivalent of that. Um, but they look at this and they say, well, there's no way that that $30 a share stock is going to go up to 60 or more in the next 3 months. That's just too big of a move. So they looked at it as an impossible event. How much are they going to charge him to enter this contract with them? Maybe they should be charging him $4 for this contract. But he offers them $2. They say, yeah, why not? It's free money. What do I care whether I get $4 or $2? I'm gonna just get this money for free anyway. And whatever, 90%, 95, probably 99% of the time, they just got their free money. They just got their free $2. They're happy with it. They walk away and think, what a goof, he paid me $2 betting on something that's never gonna happen. But that, 1 in 100 times or maybe 1 in 1,000 times that stock did shoot up for some crazy reason and went to $80 a share, and now he makes $20 a share on every share under that contract. He paid a bunch of $2 on bets that didn't pan out and made a whole bunch of money. He was able to enter these contracts, let's say, for half of what he should have been able to, because people look at impossible events and they just say, oh, it's impossible, it's free money. They don't really care whether they're getting a quote free $4 or $2. They undervalued the risk of that extreme outlier event. And he was better at valuing the risk of those extreme outliers, and he leveraged that and was able to build a hedge fund off of it. So another question, this one is less of a trick question. You can enter one of two lotteries. Lottery A, an 80% chance of winning $4,000, 20% chance of zero, or lottery B, 100% chance of $3,000. Now here, if we look at this, on average, A yields a better result. The average winning under lottery A is about $3,200 per play. And of course, the average winning on B, while there's no variability here, it's just going to be $3,000. So the return from choice A is better than the return from choice B. But under choice A, I have a non-trivial chance of just walking away with nothing. I would view this as basically paying $3,000 to enter a lottery where I have an 80% chance of winning $4,000 and a 20% chance of losing all my money. I probably wouldn't take that bet, right? People tend to choose B. So it's not just the average or the expected value or the average rate of return that we care about in any kind of financial decision or even practical life decision. We also care a lot about the risk, or really our perceived risk, and particularly the downside risk, right? What's the chance that something bad happens and I regret this later? So risk is quite important in our decision-making process, as it should be. And looking at a probability example, now keep in mind this is a Kahneman-Tversky example. So this was from the 70s, 50 years ago. The social landscape was a little different then, but this was their narrative. Linda's 31 years old, single, outspoken, very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and she participated in anti-nuclear demonstrations. And the question is, which is more likely? That Linda's a bank teller, or that Linda's a bank teller and is active in the feminist movement? So which of these is more likely? Most people actually pick the second one, but it actually has to be the first one, right? So anytime that I add an extra criterion on, that makes it less likely for that event to occur, right? Well, so satisfying one criterion versus satisfying that criterion and also a second criterion. When I add the second criterion on, that's less likely to. Um, wait, I didn't catch that. Sorry, I didn't quite understand what you were saying. So, okay. Um, so anytime that we have a situation where we have uh, probability of event A versus probability of event A and B, well, probability of event A and B has to be lower because we have to satisfy two constraints, the original constraint plus an additional constraint. Now, there are kind of two ways to look at why people would choose the second over the first. One of them is that maybe there's just a misunderstanding of statistics, right? That they choose the second one because it fits the narrative, it fits their kind of picture of Linda better than the first one. I think that's probably the more likely explanation, at least based on their research. Another is that we might be implicitly throwing in there additional criteria that aren't actually explicitly stated. So I might look at this narrative in these two events, and I might implicitly somehow think to myself, well, Linda's a bank teller means Linda's a bank teller and is not active in the feminist movement. But that's not actually what that event says, though. So we have to be, number one, very careful about the language, what exactly is being said in this event versus that event. And number two, have to be very careful about the statistics, that we don't fall into this representativeness fallacy. Okay, so kind of a short recap. The idea of subjective probability, that it's kind of a non-calculated or a non-explicitly calculated, more empirical form of probability, probably includes a lot of personal bias. We can't really depend on it very well. People are not robots that are statistical computing machines. Um, we don't deal with things like outliers um, or very specific probability statements very well intuitively. Empirical probability, so looking at big sample sizes and using that to estimate the underlying probability distribution. If we have a lot of data, probably does a pretty good job of approximating kind of the meat or the middle of the underlying distribution. But the outliers, the tails, probably doesn't do such a great job. I would need an enormous amount of data to get a lot of information about the outliers. And as far as I know, nobody has really good methods for analyzing true risk, since kind of the true risk is really in those tails. It's like the chance that something really bad happens. That's probably what we think of as really the true risk in a certain situation, like the worst case scenario. But when we say worst case scenario, we never really mean worst case scenario. Like worst case scenario is like whatever, we detonate all of the nuclear bombs on the Earth all at once or something like that. So really what we mean is something like worst reasonable case, like, you know, what's the 1th percentile or something like that. Um, and we don't really have good methods for getting a handle on those extreme edge cases. We would just need so much data to kind of fill in those tails confidently, and we typically don't have that much data for most things. Okay, so little diversion there. Hopefully that broke up the monotony of the purely mathematical addition rule and then going into the multiplication rule. Any questions on anything to this point? Okay, give me 1 second here. Okay, so moving on then to the next topic, the multiplication rule. So kind of similar to the addition rule, we have some prerequisites that need to be handled first, but let's just remember the addition rule. The addition rule was related to or, and roughly speaking, it turned or into plus. And we were concerned with whether two events were mutually exclusive. In other words, whether or not they share any outcomes in common. And the addition rule was probability of A or B equals probability of A plus probability of B. And if we do not have mutually exclusive events, then minus probability of A and B. The multiplication rule has a lot of parallels to the addition rule. When we have two different ideas that have a lot of parallels, that there are pluses and minuses to that. The plus is that we have kind of a certain structure and where we just have a repetition of that structure. So um, you know, we might be able to remember things a little bit better. We might be able to understand, if we understand one, we might be able to understand the other a little better on that basis. But the downside is that if two things look similar, it's easy to get pieces of them backwards, right? It's easy to think, oh wait, does mutually exclusive go with addition rule or multiplication rule? I can't quite remember. Okay, so multiplication rule cares about whether or not the two events under consideration are independent. So if the two events are independent, we have one form of the rule, not independent, we have another form, similar to the addition rule. What does it mean for two events to be independent? Well, two events are independent if the knowledge that one occurs does not affect our estimate of the probability of the other occurring. So for instance, if I have the same coin, if I flip it and get heads on the first flip of a coin, that knowledge that I got heads on the first flip doesn't affect my estimate of getting a heads versus a tails in the second flip. Those would be independent events, independent flips of that coin. Or something like getting a 6 on a die roll, then drawing a king out of a deck of cards. One is not going to affect the other. Events that are not independent might be something like, you know, it's snowing outside versus it's below 30 degrees Fahrenheit outside. I mean, it could be below 30 and not be snowing, or maybe it could be snowing and be a little bit above 30. Maybe the snow gets made up where it's a little bit colder and then falls down and doesn't melt by the time it hits the ground. But we certainly know there's a relationship there, right? It's more likely to be snowing if it's less than 30 degrees outside, and it's more likely to be less than 30 outside if it's snowing. So the knowledge that one event occurs affects our estimate of the likelihood of the other event. If I have two events that are independent, then when I'm investigating probability of A and B, probability of A and B becomes probability of A times probability of B. The and kind of turns into a times. So and kind of is related to times, and or is related to plus. So if we think of the Linda's a bank teller or Linda's a bank teller and is active in the feminist movement, well, if I append a criterion, so I go from event A to event A and B, if these are independent, then I'm multiplying by a probability. The probabilities are always between 0 and 1. If I multiply by another probability, unless the probability is exactly equal to 1, any other number that's strictly less than 1 will make the overall probability lower, because I've taken an original number and multiplied by a number less than 1 that makes it smaller. So what's the probability of rolling a 3 and picking a queen out of a deck? I guess I switched from king to queen between the two slides. Well, we first ask, are these independent? Yeah, these are independent. If I know that I succeeded in rolling a 3 or failed in rolling a 3 on the die roll, that's not going to in any way affect my likelihood of pulling a queen out of the deck of cards. So then I can ask, okay, what's the probability of rolling a 3? That's 1/6. What's the probability of drawing a queen out of a deck of cards? That's 1/13. So what's the probability of rolling a 3 and getting a queen? That's 1/6 times 1/13 because they're independent, or 1/78, or about 1.3%. If we ask a question like, what's the probability of rolling a number greater than 2 on, say, one roll, and then rolling a number greater than the first number on a second roll, these are not independent, right? If I fail the first event, if I roll a number less than or equal to 2, if I roll a 1 or a 2, it's relatively easy, it's relatively likely to roll a number bigger than that on the second roll. It's easier to roll a number bigger than 1 or 2 than it is to roll a number bigger than a number that's bigger than 2. So if I rolled a 3, 4, 5, 6 on the first roll, it's going to be harder or less likely to roll a bigger number on the second roll. So we can't use the multiplication rule for independent events on this. Now, that's not to say that we couldn't figure out the probability or that the probability doesn't exist or something like that. The probability certainly exists, and by the end of this chapter, we should be able to figure out the probability for this if we wanted to. But it's just that we can't use the multiplication rule for independent events to figure out this probability. Or as I mentioned, what's the probability it'll say snow and the temperature will be less than 20 degrees? Well, these are not independent events. I wouldn't want to just look over the span of a year and say, how many days is it less than 20? How many days does it snow? Find those probabilities and then multiply them. These are dependent events. As a more general rule for the multiplication rule, if our events are all independent, so if I look at event A and B and the knowledge that A has occurred doesn't affect my estimate for the likelihood that B occurs, and I can say the same thing about A and C, or A and D, and B and C, and B and D, and so on. If every pairing of events under consideration is independent, then I can say that the probability of event A and B and C and so on is just the product of their probabilities. And I actually have a similar generalization for the addition rule too, even though we didn't explicitly state it in the slides, that if all of the events are mutually exclusive, if there's no shared outcome between any pairing of two events, then probability of A or B or on down the line is just the sum of the probabilities of the individual events. So we have a similar generalization for the addition rule if they're mutually exclusive events. So addition rule with mutually exclusive events works really nicely. If I had something like this and I had to consider all of the different ways that I could overcount and subtract those all off, it would be quite a mess. Even going up to 3 events is pretty challenging. If I do A or B or C, I think I need to do probability of A plus probability of B plus probability of C minus probability of A and B minus probability of A and C minus probability of B and C. But now I think I've undercounted the overall intersection, so I think I need to do plus probability of A and B and C. Like, so for just 3 events, if I don't have mutual exclusivity, it becomes a mess. And you can imagine 4 or 5 events um, is a huge pain. So, but when we have mutual exclusivity or independence, things just work really nicely, even with lots of events. Okay, so one example over here, a coin is tossed 5 times. What's the probability of getting at least one tail? Well, the first thing we can do is we can realize, okay, well, if I think of sequences of 5 tosses, there are lots of sequences where I get at least one tail. You know, tail and then 4 heads, or heads, heads, tails, heads, heads, or 3 tails and then 2 heads, or tails, heads, tails, heads, tails. There's lots of examples where I get at least one tail. But if I look at the complementary event getting no tails, that's a much easier event to understand. Let me switch to my complementary event. Probability of getting at least one tail on 5 flips is 1 minus the probability of getting no tails on 5 flips. But how many ways are there to get no tails on 5 flips? I've got to get a head on every flip. There's only one outcome that has heads, 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 heads. So 1 minus probability of all heads, or that's 1 minus how many outcomes have all heads? Just 1. That's the outcome heads, 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 heads. How many total outcomes are there? There are 2 to the 5th, or 32. So I can either look at number of outcomes in the event over number in sample space, 1 out of 32. Or I could look at this instead as, I can look at it instead as probability of getting ahead times probability of getting ahead on the second flip, and so on through the 5th flip, right? In other words, probability of heads on flip 1 and heads on flip 2, and so on, and heads on flip 5. Well, that's just probability of heads on flip 1 times probability of heads on flip 2, and so on. Or that's just 1/2 times 1/2 multiplied by itself 5 times. This also gives me 1 over 32. So I could choose to look at it from either perspective, whichever one is easier for me. And then of course I do 1 minus that to get 31 over 32. Any questions so far? Okay, so suppose that a hard drive has a 2% chance of failing in any given year. You choose to back up your data onto an independent hard drive. So we're assuming independence here. What's the probability that both drives fail in a year? Probability that both fail is probably the first one fails and the second one also fails, or that's probably the first one fails times probably the second one fails. Well, that's each of them has a 2% chance of failing and they're independent. So that's 0.02 times 0.02 or 0.0004, 4 in 10,000 or 1 in 2,500. Right. Probably the both fail is probably first fails and second fails, which we can break up using the multiplication rule for independent events because we assumed independence between the hard drives. So under our model, probability that they both fail and we lose our data is 1 in 2,500. Now, it's a fair question to ask, okay, we have a model. Does this make sense to assume independence in, say, some real life scenario? Well, that depends on a lot of things, right? Is it likely that any real life scenario is going to be completely independent? Probably not. But if I have, if I have the same data stored on two hard drives, I mean, at the very least, the data is going to be the same. So if I like downloaded a virus that corrupted my hard drive, well, that virus is probably going to be on my other hard drive too. So there is a lack of independence there. If I keep them both like in the same room of my house and something that room floods or has a fire or something, maybe that's less independent still. If I like have one at my house and one in a safe deposit box at the bank, well, that's probably a little more independent, but now I have to go to the bank to get my hard drive. That's kind of inconvenient, right? So how well does this assumption of independence apply to a certain real life scenario? Well, that's a fair question for discussion. But as far as the model itself, the model is um, we assumed independence, so we can give the answer of 1 in 2,500. In real life, we might also be concerned with the order that the hard drives fail, right? If I have my main hard drive and my backup one, if the backup one fails first, I might not know that. And then my main drive fails. And when I go to plug in the backup one, it has failed and I lose my data. If my main hard drive fails first, and then I go and get the backup one, and you know, when my one hard drive fails, I'm probably going to buy a second hard drive and replace it. So if my main fails first and my backup one hasn't failed yet, and I plug in and I still have all my data, I transfer it to the new hard drive. So I'm less likely to lose my data that way, right? Maybe we should be asking, like, I have a regular hard drive that has a 2% chance of failing in a given year, and I have a backup hard drive that has a 2% chance of failing in a given year. What's the probability that the backup hard drive fails and then my main hard drive fails, right? In any kind of situation like this, we have models. Those models capture some component of the real life scenario, hopefully, but there are always going to be caveats. There are always going to be drawbacks. There are always going to be, there's always going to be a little bit more that we can add into the model to maybe capture more aspects of the real life scenario. And I think that's an important point. All models are wrong. Some models are useful. At what point do you stop increasing the complexity of your model because either the model is getting too complex or because you're simply satisfied with the result? You say, this is close enough for what I care about. If I had to, put in 10 times the amount of effort to get 1% more accuracy, that might not be worth the trade-off. If I had to put in 10% more effort to get, to cut my, say, potential error by a factor of 10, maybe that is worth it. So, but as a model, this would be the answer. How well does this model kind of transition to being able to explain something about actual hard drives in the real world? Well, that's going to depend on a lot of factors. So that's where a lot of that, human side of things, that kind of decision making really comes in probability and stats. Okay, so this is probably the last problem that we'll do today. So another example of multiplication rule for independent events. So here we're thinking of a scenario in a clinical laboratory, and I'm taking this as just again, like a theoretical model scenario. I'm not saying that this is how clinical labs actually run or operate, and there are certainly a lot of things that would have to work properly as far as the science and the chemistry and the biology and so on are concerned, for this to actually make sense. But we're kind of assuming that all of that does actually work out. So our scenario is that clinical labs can save money by combining patient samples to test for the presence or absence of a given disease. And the idea is that, say that, maybe I'm testing a patient to see if they come up positive for COVID or come up positive for influenza. So if I take, patient 1 and patient 2 and 3 all the way out to, say, patient 10, I could test each one of them independently, or individually, I should say. Could test each one individually and see whether they come up positive or negative. And the way that these tests work is effectively they look for some evidence of the virus or the bacterium or whatever it is in the sample. Maybe they look for a chunk of DNA that's kind of specific to that virus or bacterium. Maybe they look for something else related to it, but they look for some evidence of the presence of that in the sample. So not looking so much for amount of it in a sample, but just the presence of it. Right. So it's not the same as like a glucose test. Like everybody has glucose in their blood. Um, and what we're concerned with is the level in your blood versus somebody else's blood. Not that kind of a test, just looking for presence or absence of a viral particle, say, in the blood. Well, if this happens to be a disease that I think is kind of overall at a pretty low prevalence in the population, it's unlikely for any given patient to come up positive. What I end up doing is recording a whole bunch of negatives. And now I've spent 10 units of reagents, of lab chemicals. I've spent 10 units of tech time, of machine time to get these 10 negative samples. What I could have done instead is I could have pulled them together into a big pool. I could have taken a part of patient 1 sample, a part of patient 2 sample, and so on, put them in a big pool, mixed it all together. And as long as my assay is sensitive enough and the chemistry works out, the biology works out, all of that kind of stuff, as long as all the science works out okay, I could test this entire pool. And if I see that the entire pool is negative, if I see there's no evidence of virus in this pooled sample that consists of all of these 10 people samples, then I can be confident that all of the patients are negative. So I could use, say, maybe something closer to one amount of tech time and one amount of laboratory chemicals and one amount of laboratory machine time and get a negative test result for 10 people if the pool test's negative. I could save, lab chemicals. I mean, during the height of COVID, that was a really big deal, saving these reagents and saving even things like the pipette tips and things like that, so trying to minimize the use of those as much as we could. Now, of course, if the sample tests positive, I don't know. I mean, maybe it's just patient 1 that was positive and the rest are negative. Maybe it was patients 3 and 8 that are positive and the rest are negative. I don't know which patient is positive. So I would have to search for the patient that was the positive one. But this is what we're looking at. We're looking at this idea that if we pull together 10 patients and the prevalence of the disease is 1 in 1,000, so there's a 1 in 1,000 chance that any individual patient has the disease. we're also assuming independence, so we probably wouldn't want to like apply the same analysis if all 10 of these patients were off the same like hospital ward or from the same household or family or something like that. But our question is, what's the probability that this pool would test positive? And not given that I know the patients are all negative, but given that I don't know the patient's positive or negative status. So the probability of the pool tests positive, the probability that that's the probability that at least one of the patients in the pool is positive. But again, there are lots and lots of ways that at least one patient could be positive. It could be patient one is positive, the rest negative, patient two positive, the rest negative, and so on. Or maybe patients 3, 5, and 7 are positive and all the others are negative. Maybe all 10 patients are positive. Lots of different outcomes in here. But I could make this 1 minus the probability of the complementary event. 1 minus the probability that the pool is negative. But again, presuming that all of the science works right, the chemistry, the biology, and everything, the only way the pool is negative is if all patients are negative. In other words, patient one is negative and patient two is negative, and so on down to patient 10 is negative. But we assumed independence between the patients. So this is 1 minus probability of patient one is negative times probability of patient two is negative. And so on down to probability of patient 10 is negative. Or this is really just because the probability that an individual patient is negative is 1 in 1,000 for every patient. This is really just 1 minus, or I'm sorry, probability the patient is positive is 1 in 1,000 for every patient. So this is 1 minus probability that a patient is negative to the 10th power. And this is 1 minus probably the patient is negative is 1 minus probably they're positive. So this is 1 minus 1 over 1,000 to the 10th. Let's bring up our calculator. Or that's about 0.009955. Or this is about what? It's about 0.01. 1% or about 1 in 100. Now, something to note, if we weren't thinking carefully about this in terms of probabilities and all of our different rules and everything, we might have naively looked at this and said, well, each patient has chance 1 in 1,000 of being positive. I have 10 patients. Maybe the chance that the pool is positive is 10 times 1 in 1,000 or 10 in 1,000 or 1%. We actually see that that wouldn't be a bad approximation here, but it's not exactly the right answer. In this case, that would be a fine approximation to do. We would get very close to the right answer. If the sample contained 100 patients instead of 10, what would change? Well, we would go out to patient 100 here. That would change this to 100 which would change that to 100. So just instead of to the 10th power at the very end here, we have the same stuff all to the 100th power, or that's about 0.095. 9.5%, where our naive approximation would have been, say, 100 over 1,000 or 10%. 9.5% versus 10%, not off by a ton, but that's still a half a part on a scale of 10. So that's like 5% error. That's maybe not a trivial amount. Okay. So okay, I think that's as far as I want to go with that problem. An interesting question. Maybe I'll pose this as a question and also post it to the um, I'll also post it to the Blackboard site. You can give it a thought, and then maybe we'll warm up with this on Monday, and then move forward with this presentation and start into part 3. So, interesting question. If the pool is positive, well, one approach would be if the pool is positive to just go and test every individual in the pool and see which person or people are positive. But if the pool is positive, I mean, this is a pretty unlikely disease, 1 in 1,000 chance of occurrence. There's probably only one person in the pool that's actually positive. We have a pretty good chance of that happening. If we did not want to test every person, because that uses a lot of reagent, that uses a lot of equipment time and so on, if we assume only one patient is positive, how could we search for them? In other words, how could I efficiently find the one patient that's positive by doing the fewest number of follow-up tests? I could just test everyone, right? If I had a pool of size 10, I could just do 10 tests, test each patient individually. I could get the answer with 10 more tests. Could I get the answer using a similar idea to what we've done here? Could I get the answer in fewer than 10 tests? Assuming only one patient is positive. So maybe give that a thought for next time. I'll post a little diagram on the Blackboard site and make that available so you can look at that. That kind of lays out the same question in a slightly different way that might be a little more helpful, kind of lead you to the answer a little better. And then we'll pick up here on Monday. So I'll stop the recording.